So for the z interval, the confidence interval for the mean using a standard normal distribution, if we know sigma, the margin of error is this critical, what we call a critical value, z star times sigma over square root of n. Now z star itself is the value that if you look at the standard normal distribution, remember z tells you you're looking at the standard normal distribution, which is centered at 0 and has a standard deviation of 1. Well, z star is the value that you would need to go out in both directions, to where between negative z star and z star, the area is whatever your confidence level is. If you want 95%, you would need to have 0.95 be the area in between negative z star and z star. Okay? If you wanted a 90% confidence interval, you would need 0.9 to be the area between negative z star and z star. So what we're really doing in the formula is we're doing that for the standard normal distribution, and then we're multiplying by sigma over square root of n, which converts it back to the distribution for x bar. So what do we say here? Since these are z-scores, they tell us how many standard deviations above and below the mean you would need to go to trap a certain proportion of the population. And then, as I said, multiplying by sigma over square root of n will convert that back to the normal distribution centered at mu with sigma over square root of n, so x bar's distribution. We can find that. I've written a couple of different formulas here. The second one's probably the easiest one to think about. We could find z star here by figuring out this area. It's probably easier to find negative z star, or find the z value here and change the sign. If you think about the picture, you've got c% in the middle. And I'll show you some examples with actual numbers here in a minute, but we've got c% in the middle. Let's say we got 90% in the middle. And then if you do 1 minus that, you would have what's in the tails. So if you have 0.9, you'd have 0.1 in the tails, or 90% in the middle, 10% in the tails. Divide that by 2, and you have the amount in each tail. So if we take our percent as a decimal, subtract it from 1, and divide it by 2, you get what's in each tail. Okay? So subtract from 100% to get what's in the tail, in both tails, and divide it by 2. So if I do inverse norm of the standard normal distribution, I use 0 and 1, and I use the value that's in this lower tail, I would get negative z star, and I just change the value to get z star. Okay, so there's a way with the calculator you can compute it. And again, I'll do it for some specific values in the examples. And put the note up. So I've said this, but let me read it one more time. So c% of the sample mean values of our original variable lie within z star times sigma over square root of n of mu, or in other words, c% of the samples mu and x bar are that close to each other, z star times sigma over square root of n. So that gives us an interval that c% of the time x bar and mu are going to be that close, and we're going to capture the mean. So again, that's our formula. We can write it with a plus or minus, but we have a lower bound of x bar minus z star sigma over square root of n, x bar plus z star sigma over square root of n. Okay. As I said at the beginning, there's a lot going on here, so let's focus. Let me kind of reiterate. The big concept here is, because we know what the sampling distribution of x bar looks like, there is a procedure where I can find what's called a confidence interval. And whatever the confidence level is, C, which could be 95%, 90%, 99%, whatever you choose, and that's going to determine what the Z star is in the formula. But whatever your confidence level is, that percent of the time, your interval is actually going to contain the true parameter mu in this case. Okay? So if I do a 95% confidence interval, well, 95% of all the confidence intervals of that sample size would actually contain mu. The one we find may or may not, but if you think about it as before I do it, I got a 95% chance by random sampling that I will find one that works. So we're fairly confident. So you want your confidence level to be really high. In terms of the mechanics, the formula is x bar, your sample mean that you find in your sample, plus or minus to get the lower and the upper bound, this critical value, z star times sigma over square root of n. So this part, z star times sigma over square root of n, we call that the margin of error. Sigma over square root of n, that's the standard deviation of x bar using sigma and n from your sample size, and sigma being the original variable x, that's standard deviation. And then z star is this value that captures c% of the standard normal distribution in the middle of the picture. Okay. So let's do an example. Okay. Suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. So to do the z intervals, we have to know sigma. So sigma is 3. We have a random sample of 36 scores is taken, so n equals 36, and it gives a sample mean of 68. So our sample mean score is 68. Find a confidence interval estimate for the population mean exam score, the mean score on all exams. So find a confidence interval, and we have to have a confidence level, so we're going to do 90%. So in other words, we got this information here. We're going to do a 90% confidence interval for the population mean using a sample mean of 68, a sample size of 36, and sigma being 3. So we've got n equals 36, that's the sample size. We've got x bar is 68, and we've got sigma is 3. The only other number that's missing in the formula is the z star, okay? Because our formula is x bar plus or minus z star sigma over square root of n. So we need to find z star. Okay? There are tables for the common values of z star you could look up if you were doing this and you had access to those, but we can find them with inverse norm. Okay? Here's the picture. I always draw the quick little picture if I want to find this with my calculator. Draw yourself a bell curve. Think about your confidence level. If it's 90%, we got 90% in the middle there, or 0.9 if we did a decimal. That means there's 10% split in the tails, so there's 5% in each tail. So I can take my calculator and do inverse norm. Remember, inverse norm, you give it the area to the left. So if we're looking at negative z star here, we could do inverse norm of 0.05. I have to do 5% as a decimal, so 0.05. And then z is coming from the standard normal, so I use 0 and 1 for mu and sigma here for that distribution. If I did that without the negative, I would get negative z star, and I would get negative 1.645 something from my calculator. We round it. Usually there's 3 decimal places given in the tables for these critical values. So if we change the sign from the negative z star to z star, we've got our z star is positive 1.645. Here, I'll compute it with the calculator to review how to do that. Okay, so I'm emulating the newest version of the TI-84, being the color edition and everything, but any version of the TI-83, 84, we can do this. I'm going to clear my home screen. So I draw the picture first to figure out the area there would be 0.05, and then do second variables, which has distributions above it, and we do inverse norm. And you give it the area to the left of negative z star there would be 0.05. Have to give it as a decimal between 0 and 1. And then I use 0 and 1 for z star. That's standard normal. Use 0 and 1. I'm going to paste that. And again, if you didn't get the menu, it just pops up inverse norm, and you type those numbers in that order. Your area, comma, mu, comma, sigma, and for standard normal, it's 0 and 1. Hit enter, and there we go. So negative z star would be negative 1.645 if I round it. Positive z star would be 1.645. So we have all the numbers we need. Let's see. Sorry, I accidentally clicked back and animated them away there. And then you just throw everything into the formula. You could do it all at once. Sometimes questions will ask you for the margin of error first, so that's the way I did it. The margin of error in the formula is the z star times sigma over square root of n. So we figured out using inverse norm that z star would be 1.645. Sigma was given as 3, n is 36, so we divide by square root of 36, or 6, and we get 0.8225. So that's what we call the margin of error, and then we take our sample mean that we found of 68, or it was given to us in the problem, but someone found it from the data. We subtract the margin of error, and we add the margin of error to get the lower and the upper bound. So we get 67.1775, rounding to 4 decimal places, and an upper bound of 68.8225. So I'll do that on the calculator in a second using the built-in z-interval command, but first of all, let's interpret what did we just figure out. Okay? So we have an unknown mean, mu, but somehow we know the standard deviation is 3, and we have a sample of a certain size and a sample mean of 68, which is always in the middle of the interval you find. Your sample mean, it's built around the sample mean, so it's always right in the middle. But we're 90% confident that the actual mean is somewhere between, let's say we round, between a 67 and a 69 if we rounded to 1 decimal place. Okay. And again, what that means is maybe it's in there, maybe it's not, but the process, there's a 90% chance when we do the process that the interval we find works. Okay. I had a professor one time when I was at UGA that did not like you to say there's a 90% chance that the mean is in here, because he would claim there's either a 100% chance or a 0% chance, because either it is or it isn't. That you're kind of just, you might say it's semantics there, right? Depending just the way you're saying it. The process has a 90% chance. If you think I'm going to consider that I could find any possible random sample, Well, if I find one, I got a 90% chance that I found one that works. Either it does or it doesn't, and we don't know that, but we say we're 90% confident that it does. Sorry, this video is getting a little bit long, but we're almost done. Let me just use the calculator and show you how to do z-interval to find that. As we go through the class, we're going to do more and more hypothesis tests later, and we'll do other types of confidence intervals. We will do the t-interval for the mean, where you replace sigma with s, and there's a slightly different distribution behind it. We will do confidence intervals for the difference between two means. We will do confidence intervals in different situations. Okay? And as we move on, we'll rely on the calculator mainly. But I do expect you to be able to do the z-interval by the formula, to know and do the formula, because it's not too bad of a little formula to remember, because we need to remember anyway the central limit theorem that x bar has mu and sigma over square root of n, so you have that sigma over square root of n part. And so you remember the margin of error is z star times sigma over square root of n. And I want you to really understand what z star is and how we do this. So I would like you to be able to go through that process for the z-interval. But you can check the answer here really quickly on the calculator. Let's see, this one, we go under the test. You hit the stat button and go over to the last column with the arrows there to tests, and all of the inferential statistics we're going to do in this class, hypothesis tests, confidence intervals, all these different things you'll see here in this table. We're going to talk about most of them as we go along. Right now we're doing the z-interval, which is number 7. So you can either scroll down and hit enter or just click 7, and it'll pop you into a menu. So you get a choice at the top between data and stats. If you have the actual data, say we had the 36 scores, I could put those in list L1 and use the data and tell it that. And we'll do some problems where we have small sets of data. But what we have are the summary stats. If you have x bar and sigma and those numbers, click on stats. And then you enter in the values. So given in the problem, sigma was 3, and then x bar was 68, and the sample size was 36. So that's n, and the confidence level, you have to give it as the decimal between 0 and 1, 90% is 0.9. And then click calculate, and it'll do what we did, and instantly, though, spit out the answer there. It rounded it so that it could fit it on the screen to 3 decimal places, but you're going to see it matched what we got, 67.178. If we round, we got an extra digit by doing it by hand. And then 68.822. Looks like we're off in the thousandth place. Our way was more accurate because we carried more digits. But anyway, actually, no, I'd say the calculator is more accurate. We rounded the z-star. But we're matching it to, at least I usually round to 2 decimal places in the end when I do these anyway, unless we're talking about really small numbers that are in decimal digits already. But either way, we do it with the calculator or by hand. We've got pretty much the same answers there. So that's how you do the z-interval with the calculator, and it was in the stats menu, stat. When you go to calc, that's where we get our descriptive statistics and our regressions and those things, but go over to test, and there's all the hypothesis tests and confidence intervals.